Hi, welcome to the universe of first-order RC circuits. In this video, we'll show you how you can solve differential equations using the famous Laplace Transform. In here, you'll find math formulas, some illustrations, and graphs, so you can pause the video whenever you need a little bit more time to let the information sink in. Let's do this! Cutting things short, the Laplace Transform enables us to transform differential equations in the domain of time into algebraic equations in the domain of frequency. Remember that in algebraic equations, the unknowns are only submitted to algebraic operations. Here are some examples of the application of the Laplace transform and its inverse transform. Take a look. Now, take a peek at some of its properties. In this video, we will focus on the Laplace transform applied to the computation of UC regarding the forced response of a first-order RC circuit. You can refresh your memory by watching the video Forced Response of a First-Order RC Circuit. Let's recap. In that circuit, there is a voltage source and a switch in series with a resistor and a capacitor. The switch, K, is initially open, ensuring that the capacitor current, IC, is zero and its voltage, UC, remains constant. The capacitor is completely discharged at time zero. At that instant, the switch, K, is closed and remains closed from that moment on. We want to know how the voltage and the current behave from that instant onwards, that is, for t equal or greater than 0. You already know that the forced response of a first-order RC circuit is defined by this equation, where E, R, and C are constants. Applying the Laplace transform to both members of the differential equation, we get the following algebraic equation, where, obviously, we no longer have derivatives of UC. This equation can be rewritten in this manner. But then, how do we determine A and B? Well, firstly, the two fractions are reduced to the same denominator. Multiplying the numerator and denominator of each fraction by the denominator of the other fraction, as we can see happening in here. Then, knowing that the sum of the new fraction numerators equals 1, A and B can be determined. Therefore, the following expression is obtained. Finally, to get to the solution of the differential equation, we must apply the inverse Laplace transform to both members of the latter expression. This analytical solution for the voltage UC allows us to determine the exact value of UC of TA, the value of UC at time TA, without resorting to values of UC at times prior to TA. Thank you so much for staying with us. Keep exploring this universe by watching the other videos we prepared just for you. See you next time, and good study session!